Hey there, this is Philip Arroyo, and I appreciate you joining me in a introductory building construction class. So this is not necessarily a class that will allow you to go out and build a home. Obviously, there's a lot of permitting, a lot of construction methods and rules and so on and so forth that allow you to do that type of work. But what this does, it will prepare you as a firefighter to understand building construction and how it impacts our response and our tactics and our awareness. Again, this is introductory. Probably many more hours or days that you can do on training, and I encourage you to do so. This is not one of the most fun classes that are out there and offered, but I think these are one of the most important classes to truly understand fire and how things burn. So bear with me. This will be the first time we do a recording on a training class like this. And of course, if you have any questions, please reach out. Call me, email me, text me, and let's try to get this question answered. So again, let's jump right into it. So the objectives from this PowerPoint and utilization of photos and just dialogue here is to describe the characteristics of the following building material. We're going to talk about masonry, concrete, steel. We're going to talk about glass, gypsum board, also known as oh gosh, throwing a blank already. Sheetrock, also known as sheetrock, and obviously wood, common construction material used in building homes and so on. We're going to list the characteristics of each of the following types of building construction. We're going to talk about fire resistive, non-combustible, so your type 1, your type 2, type 3, ordinary construction, type 4, heavy timber construction, and type 5 wood frame construction. I encourage you to really pay attention in that area. Many questions on the exam, certifying exams ask questions just on those themselves. We're going to describe how each of the 5 types of building construction react to fire, and we're going to describe the functions of each of the following building components: foundations, floors, ceilings, roofs, trusses, walls, and then we're going to have some additional tidbits at the end regarding collapse and other kind of things that you need to know as firefighters. So, quick introduction. We in the fire service, us as firefighters, need to remain students of this trade. We need to constantly be training and constantly be going to training, constantly be hearing what other people are saying so that we can learn. The method or the saying is out there that once you stop learning and once you think that you know it all, it's probably a good time for you to get out of the fire service, because you become a very dangerous person if you think you know it all or felt that you've gone through all the training that there is. We need to constantly be training. And that said, this PowerPoint was partially created a couple of years ago, and each year I have to add on new things because just in a year's worth of time, there's new techniques, new technologies, new construction methods, and there's a lot of folks always doing research that bring new things to light that we didn't know at one point. And this is why we need to continually be training on these things so we can stay on top of these technologies. Maybe one thing that you learn on one of these slides could save your life. And so if we're constantly being exposed to other trainings out there, those items may one day save your life as well. So similar to fire science, we covered fire science on a previous class. In fire science, we went in depth all the way down to the molecular level. And similar to that, in understanding fire science, to be able to extinguish it, very similar to building construction, when we understand how something is built, how it's tied in, the materials and stuff, we can predict how fire will spread. We can make good, knowledgeable safety decisions about structural integrity or lack of structural integrity, and we can obtain a snapshot of potential layouts inside before we would make foot on it. And this is pretty neat. We can predict what a house kind of looks like just on our approach to the scene. Now, you haven't gotten to this point yet in firefighting, but we often teach that we really need to be looking at the structure on our arrival. So, you're looking out that window for a reason. As you're getting dressed, as you're putting your helmet on, your mask on, you're looking at that building so it can offer you some sort of clue about what you're about to get yourself into. So we go to this following slide, and I just have a photo here that I took off of Google. But this photo shows a house very similar to something we may find in our area, with the exception of, I believe this has a basement. So we will ignore the basement portion of this, but otherwise everything above the ground looks like a normal home in our area. So if you were to pull up on this fire, if this house is on fire, if you pull up on this house on your engine and you are a firefighter, there's a lot of things you can already tell just by looking at this house. So obviously, we can look at that there's two garages, or two garage doors. That is, it's probably a single garage opening, but with two garage doors. We can tell where the front door entry is. Most likely, you can tell that the back behind this house, so that Alpha Bravo, the Charlie side of the house, probably has a rear door. We can tell that this is most likely a brick veneer structure, not a true brick house. But I may be wrong. I actually kind of see some indications that it may be a true brick house. But we know from the layout, though, that where a possible living room may be, where the bedrooms may be, just from our common knowledge, understanding of our own homes, most likely we will never find a kitchen upstairs. So we can already scratch that off the list about where might this kitchen be. This kitchen may be going right into the front door to the left, right after this little what appears to be some sort of breakfast area or dinner area. It might just be just past that on your left, or in some cases, that kitchen can be right behind that garage on the other side of where the cars would be. So small things like this helps us predict where things may be. We do know that a high percentage of time victims are found in their bedrooms. So if we were to if we were trying to develop a plan on how to make entry to these bedrooms, we know that most likely every room upstairs is a bedroom. And there may be a game room up there too, but these are just assumptions. These are not 100% facts, but these are assumptions that we can actually work off of and can be fairly credible and viable, where we can find a viable patient in there. So that is why understanding construction is important, understanding layouts, building methods. I do think that this house is not a true brick home, and the reason I say this is I look at the neighbor's house that is in the background, and I could see some siding moving down most of the house, it appears like. So this will lead me to believe this is most likely a brick veneer home, and we'll talk about a little bit more about that and how to determine both, which one's which. So materials used in construction, these are just common materials, and you'll see small writing on my slides. I've built in to these slides what the objective is from the certifying agency. In this case, SFFMA. SFMA says you need to cover certain objectives, and so I found it helpful to add those objectives onto the slide so I know exactly where to find them if I ever need to reference it. So you don't necessarily need to pay attention to that objective, but you will see them on some of the slides. So materials used in construction: masonry, concrete, steel, and other metals, glass, gypsum board, wood, plaster on lathe. I'll add shiplap right after that, and cast iron. We'll talk a little bit about more about these in depth. So masonry, brick, if you want to, is inherently fire resistive. They're poor conductors of heat. We remember from fire science, poor conductors don't allow heat to transfer through as easily as a good conductor, something like copper, where the molecules are tightly packed together, allowing heat to transfer from one molecule to another fairly quickly. Again, picture a cast iron pan on your stove being heated. If you touch the handle, the cast iron is tightly packed together with molecules, so you'll feel the heat soon, as opposed to a wooden, maybe a broom handle If you expose one side of it to a fire, you're not going to feel the other end get warm or hot because wood is a poor conductor. So in this case, masonry is a poor conductor of heat. Openings within the brick or masonry work can allow fire to spread. So sometimes the mortar or the plaster has been damaged or not well put into the joints, causing there to be gaps in there that can allow fire to spread. And with prolonged exposure to fire, so if fire is directly impinging on it for long periods of time, masonry can collapse. And I've pulled some research into this slide, and I'll read it as such. Mortar joints often appear to be more affected by fire exposure than the adjacent surface of the masonry unit. So the joints themselves appear to be more affected than the actual face of the brick. When masonry walls are subjected to fire hose immediately after fire exposure, in this testing that they did, mortar that was in a dehydrated state is sometimes flushed out, typically to a depth of about 1/4 inch. In actual fires, though, mortar joints subjected to the most severe fire exposures can become softened or chalky, although this typical damage is not deeper than about 3/4 of an inch. So that tells us if the mortar is applied to this joint of the brick, and keep in mind there's different types of brick, hundreds of different types of bricks, some that can withstand fire and heat a lot better than others. And obviously those that can are more expensive than those that can't. So one thing that we can talk about now is just construction in general. Folks want to build these homes as cheap as possible that can still do the same job as an expensive build. But if I can do it for cheaper, that means I can gain a bigger profit as a builder. And so that's going to allow me to, well, that's going to cause me to want to buy cheaper materials that can still do the same job. Or sometimes, unfortunately and unethically, that might mean also skipping steps in construction, leaving your house in a vulnerable state. So back to this, it talked about these mortar joints being affected by fire more often than the face of the brick, and how sometimes that mortar joint is already damaged before we even start, before we even arrive, and then you add fire to it, and then you add our tactics of fire water in the area, and we may be pulling more of this mortar joint out inadvertently. That could potentially cause some collapse in this brick, right? And if this is a very tall brick wall, then we can understand how it could create a collapse issue and a safety issue for our firefighters. A little bit more about masonry. So this is again based on research that I did on this, was that degradation of materials exposed to high temperatures added to differential thermal expansion, which may bring the elements to collapse depending on the deterioration of age. So temperature, and this is not something that you don't understand. This is something common. The difference in temperatures affecting the face of the brick can be different in different parts of the brick. One area of the brick may be hotter than the other, or if you break it down to molecularly, some of those, the way the heat is hitting some of these molecules on the brick could cause part of the brick to contract, could cause part of the brick to expand, and in doing so, that increases the potential for collapse of a brick. Now, mortar has a shorter lifespan than brick. Remember, mortar is what's filling in the joint between the bricks. So mortar has a shorter lifespan than the brick, and depending on how exposed the masonry is to water and other harsh conditions like rain and heavy winds during hurricane season, all that stuff, but in typical, mortar will last about 25 years. That's not very long, not very long. Houses built in the early 2000s might be up for, might have some deterioration of this mortar already, and here they are exposed to fire and on a house fire, and then we go in and we try to put this fire out. So there's some vulnerabilities already built into the house before we even arrive on scene that we have to be cautious and knowledgeable about. Now, I have talked already about how different bricks are out there to hold for building and ovens and furnaces and all that good stuff. So different bricks are out there that can really withstand that heat of that fire much better than some of the bricks that are used in construction of our homes. But they are much more expensive. So one thing though to keep in mind, this brick fireplace does not have any mortar between its bricks. And it was purposely done that way. This is the way that they wanted to build their fire pit. But notice or keep in mind that without the mortar in between those bricks, that allows for air to go in there, right? And so in this simple demonstration, we can see that without the mortar, air can come in, fire can come out, all that good stuff, which could be very dangerous in fire spread within a house if the mortar is not in place or if it has deteriorated. Okay, let's continue on here. We have there's actually been a lot of studies on the effects of fire on masonry or in this case brick. And this is important because if I am a builder or if I am an insurance company and I want to save a lot of money on rebuilding a house after a fire, well, if I can find some research that shows, hey, your brick really doesn't get damaged, it's mostly the mortar, then why do I tear down a wall and waste all that money that I can save when I can just fill in the holes from the fire, caused by the fire, with additional mortar? So here you see in the picture on the right, someone refilling in the mortar that may have come out after a fire. You know, you give the brick a good scrubbing and pressure wash, and it'll look good as new, or you just paint over it, and you wouldn't know that there was a fire. So again, that masonry or the face of the brick itself really does a good job of not burning, and which is it is a good property of masonry. But keep in mind that mortar will be affected much quicker than the brick is. But again, in this case, simple refilling of the mortar into the brick can allow you to rebuild this house a lot quicker than having to tear this wall down and put up some more. So we talked earlier when we looked at that house about a brick veneer and a brick and a solid brick house. Okay, and so here we have two pictures of a brick veneer home on the right, and then one that is a solid masonry on the left. So the biggest difference is that with solid masonry or a true brick home, the brick is holding up the house. With brick veneer, the house is holding up the brick. Okay, so let's break that down a little bit. So let's talk about teeth. You know, you go to the dentist office and they have to put a veneer tooth in you. Okay, that veneer tooth is a tooth that looks and functions like your other teeth, but it's fake, right? And so in that comparison, the brick veneer is more of an exterior decorative thing. It's let me add the wall that looks like brick to make it look like a brick home when it really isn't. So why would you want that? Well, brick costs money. A true brick home is going to cost a lot more money. Why? Because material is more expensive. You need more bricks. Two, because a true brick home is actually pretty strong and can stand on its own without the need without a need of framing behind it. So a true brick home is ideally what many people would want to withstand the elements and just to be safer, and it's got a nice look to it. Brick veneer home, if you're trying to get the look of it but not the function of it, then you go with a brick veneer home. You save a little bit of money, a lot quicker to put up. You don't have to have as many brick masons out there trying to put this together. But notice in the brick veneer wall, your brick is being held up by the framing of your home. So the studs that are in your wall, the plywood, the moisture barrier, all that, the brick ties, all this is holding your brick into place on your brick veneer. And of course there's weep holes. Weep holes allow for moisture to exit. You know, your house sweats and breathes with the humidity and so on, and so that moisture needs to go somewhere. So if you didn't have the weep holes, then that would allow moisture to stay behind the wall and create mold and affect other structural components. So you have to have those weep holes at the bottom. A lot of people see those weep holes and want to fill them in with some type of mortar, and that's incorrect. Your house needs to be able to breathe. But again, you move over to the solid masonry picture on the left, and you can see how a lot of those bricks are overlapped. They're different orientations. The face of the brick changes to add just a different surface area, much stronger joint or joining. So that is one indicator of how you can tell a house is true brick or veneer, is by the orientation of the brick and the alternation of it and how it alternates, because that helps to add strength to the home. On the other hand, that brick veneer, you typically lay it with the same face exposed, and you just alternate it, and that gives you your appearance of a brick home. We're going to talk a little bit about concrete, and we'll go into a quick video on compression and tension. So concrete is inherently fire resistive. It's a poor conductor of heat. It's strong under compression, forces of compression, and it's weak under the forces of tension. Can be damaged through exposure to fire, and I'll show you a picture here in a little bit. And one type of damage that is often talked about is spalling, which is the flaking of the surface of concrete due to water and heat pressure, and also mechanical pressure, and there's also corrosion and all those types of pressures that affect spalling. But tension is simply defined as a pulling force exerted perpendicularly and away from the surface. So we think about the use of rebar, okay? And that rebar, like you see in that bottom photo, is helpful to move the forces of compression out and away so that your concrete is not absorbing in that. Let's say you have a huge 18-wheeler on it. Well, you don't want that concrete bearing all the weight exactly where the tires are touching. So you add rebar in it, and the rebar not only helps to keep the concrete together and solidifies it, but it also helps to dissipate the weight away from the surface. It adds surface area. So much like tension forces, that rebar helps to spread that force, that tension force, and the compression force as well, away from the area that has the load on it. Now, compression is defined as a pushing force towards a material. So we see in the diagram here with what looks like the orange columns, you see that there is compression forces, and those are normally found right just where we live at, and gravity and so on. There's always a compression force on us, and that includes material as well. Now again, we're going to go into a video real quick that will explain compression and tension forces.
Hi, today we're going to talk about the forces involved in building bridges. First, we have tension. Tension pulls on objects. As you see, when I pull on this elastic band, it gets longer. The opposing force to that is compression. Compression is when things get crushed and pressed down. As you see, when I press on this spring, it gets shorter because it gets compressed. Now, when building bridges, if you don't distribute your weights evenly, you'll have something like this. This is buckling. So it can hold the bridge, but as soon as force is applied, it just smashes, breaks under the pressure. Equally, with Lego bricks, there's tension. If I only connect one node of these two pieces and pull on them, they easily come apart. But if I attach more, it doesn't really happen. So, when building bridges, you need to dissipate the energies. So here, we'll have a bridge. and the weight isn't in one particular spot. The weight transfers up the cable through tension and presses down on these four towers with compression. Multiple spots ensure stronger bridges. That way, see, I can put a lot of weight on this bridge. And it doesn't buckle, and it doesn't snap. See, if I pull on this elastic band too much, it snaps. And then if you saw, I crushed this paper tower. So remember, overlap your bricks. Make sure there's a lot of surface area, so you make strong bridges.
So hopefully that clarified what compression tension forces are on our building materials. We're now going to move into spalling, and I showed you the image of spalling earlier on where you could see the rebar coming through. Spalling is caused by heating, mechanical pressure, or both. There's also corrosion, there's salt-related spalling, there's weather-related spalling. But in our case, we're going to talk about those caused by heating, or in our case, fire. This heat and or pressure causes uneven expansion of the materials that make up the concrete, such as sand and gravel. We got to remember that concrete is an aggregate of a lot of stuff that helps make it strong. So the reinforcing steel in the concrete mix, or the surface and subsurface layers of the concrete, are all being exposed to some sort of pressure and or heat and fires. Alternatively, or additionally, the heat may release the water in the concrete, so there is moisture in the concrete, and heating different areas of this concrete during a fire could cause spalling. Pressure created by rapid changes in temperature, such as application of cold water to the heated surface during firefighter operations, can also cause spalling. So we go in there, we're fighting this fire, this concrete's super heated and at different areas of it, and we introduce a rapid change in temperature to it. It could cause spalling, and it could cause stuff to come out, stuff to flake off. So here is a looks like a subway or tunnel, not necessarily a subway, but a tunnel where vehicles may have been driving through, and there was a large fire in there, and the temperature's elevated and heated up the concrete around it, and you began to see spalling throughout the surface of it. So then firefighters come in here to put this out, and you're adding additional pressures and additional temperature changes that cause additional spalling. And spalling is dangerous because you're breaking down a material that is used in that particular construction, and you're weakening it. So think of it as part of a system, and you're weakening part of that system, which may cause overall system failure. And you're exposing rebar, stuff that shouldn't be exposed to the high temperatures, and that rebar is expanding and contracting, and it's causing concrete downwind or upwind, or down the way or up the way, to give and release, causing additional collapse potential. So we need to be very careful with spalling. We need to be cognizant of it. We need to be aware of it. We need to be knowledgeable about the signs of it, especially on walls that are made out of concrete, like we find at many of these storage warehouses. And not all concrete is the same, just like not all apples are the same, right? Factors that affect concrete strength, it may all appear similar, but how it fails due to weather and heat and fire and temperature and firefighting and water applications can have different effects for different types of concrete. And for example, water, how much water you use, the type of water that you use in forming this concrete in the beginning before you pour it, could have an effect on how it retains its properties, its compressive and tension properties during a fire, or the type of cement that's in it, the quality of it, where it was obtained from, rock aggregates, the quality of them, purity, where it was obtained, particular size or the grade of it. admixtures. What admixtures are in this before it's poured? Admixtures could be things like chemicals and so on that can be added to it, either to change the color of it. You want something lighter, darker, redder, or let's say it's a really hot day and you don't want the concrete to dry. You want to be able to pour it and have some time to either stamp it or to shape it how you want it. So you add an admixture to it that allows that concrete to dry slower, gives you time to work with it. It increases the time you have to work with it before it dries. So if you add all these type of little things to it, it may change the properties of that concrete. It may make it more susceptible to collapse or less susceptible to spalling. Handling techniques, so how these guys and gals pour it, how they spray it. Do they do a good job of getting all the air bubbles out? Do they put proper rebar in it, the correct type, the correct size, the correct spacing? Curing conditions. What was the temperature when it was poured? Was it down here in Texas or was it up in Wisconsin? Temperatures and how it dries. Was it humid and wet or cold or snowy? Those are all things that make concrete different from one another. And then obviously the foreign material. There's always a presence of foreign material, right? I can think of pollen here recently that may get into this concrete as it's being poured. Now, is that a big thing? Probably not. But that's just a visible example of how things can get in this concrete before the pour, during the pour, after the pour, that could affect its properties. We're going to move into steel. Steel is the strongest material in common use. It's strong in both compression and tension. We saw the video and we know what that means now. It will rust if exposed to air and moisture. It's not fire resistive, but it is a good conductor of heat, much like your cast iron pot. It expands and loses strength when heated. That is a big thing to keep in mind. And any sign of bending, sagging, or stretching of steel that's used in construction and holding things up indicates an immediate risk of failure and should be communicated to incident command if you have any of those signs or symptoms of it, because it could indicate, again, that there is a collapse either at that position coming or something else that's tied into it could collapse along the way. So these are some numbers that were obtained, and I think these fluctuate as well based on how the steel was forged and where it was forged and just the materials that make it up as well. But in general, structural steel can withstand approximately 425 degrees Celsius before it begins to soften. So 425 degrees, how hot is that? Well, a simple candle, just the flame of a candle, will often burn on average at 1,000 degrees Celsius or more, while propane can cause a fire to reach almost 2,000 degrees or more. So when something is burning inside of a building, a house, or a warehouse, the fire temperature may be in excess of this 425 degrees that causes softening of the structural steel easily. Between 600 degrees and 650 degrees, the steel will lose half of its strength and will pose a risk of failing depending on the load that it bears. So we'll talk a little bit about live loads and dead loads in a little bit. And then unsurprisingly, even a house fire will reach very high temperatures of around 600 degrees Celsius or just under, sometimes more, again, depending on what material is burning, the fuel load. And of course, it depends on as I mentioned, what the material is that's burning. But we think about these temperatures that causes steel to weaken or soften, and it's not much. And much steel, steel can be either fireproofed, meaning some sort of coating put on it that won't allow it, that will resist the fire for a period of time, or it could be without fireproofing, meaning exposed. And as you can see in that picture, it looks like that steel on that open web truss system there, it looks like it's not fireproofed, and it got some temperature to it, got some heat to it, and it caused it to bend and soften. We had a fire some 5, 6, 7 years ago in a commercial building that had a similar open web steel joists like that, and on the outside were concrete walls, and these were helping. We're adding structural stability to those concrete walls, and we got some expansion of that steel. So the steel heated up and it began to expand and it began to push the walls out. And you've got to remember these walls are engineered to be straight and to have very little movement in them. And here you are causing the metal or the steel to expand, pushing those walls out in a way that they weren't designed to withstand. So it increases the potential for collapse. We noticed a sign. We noticed that there was the walls where they came together were no longer together, but one was bowing out. And what we had to do was make sure that no one was in the area firefighting, so that if and when it did collapse, they would not be under it. Other metals that are used, aluminums and so on, these are lightweight. Again, they're cost effective, but they don't withstand heat, temperature as much as steel does. So it doesn't take much heat and temperature on these unexposed aluminum parts or other types of metals that they're using nowadays, lightweight metals, for this to cause part of the construction system to fail, which may cause a collapse or an early collapse of our homes. So understanding how our houses are built, if we happen to walk into a neighborhood and they're using this type of construction, then we need to make a mental note of it, so that if it does burn, we know that we need to operate fairly quickly at finding this fire, evacuating patients, cooling the areas down so that we don't contribute to a earlier collapse than we need or want. Glass, there's different types of glass. Glass is usually non-combustible, it's not fire resistive. Various types of glass, such as laminate and tempered. You'll learn a little bit more about glass in your vehicle extrication class. But in this example here, you have, it looks like you have tempered glass separated by, not separated, but combined with a piece of laminate in the middle. Similar to what you'll find sometimes on your, typically you find laminate on your front windshield, tempered on the sides, but nowadays you can find them just about anywhere. And these windshields in this glass does add structural to your vehicle. So a lot of these newer vehicles and older vehicles, this glass is part of the structural cage of your vehicle. But I'm not going to cover much more on glass other than what I just did here. Sheetrock, also known as gypsum board. We deal with this most everywhere. Every house fire, we have some form of sheetrock. You have sheetrock in your home. Not necessarily a strong structural material. It doesn't add a lot of structure to it, but it's mainly used for finishing. It's a very good insulator, and most often is used for forming part of your firewall. Firewall is designed to keep fire separated in void spaces like your attic. So if you have multiple apartment units side by side and you've got an attic that connects all of them, hopefully the attic has various firewalls made out of gypsum that can cause or prevent fire from spreading from one unit to another in that open space. Has limited combustibility. The paper of the gypsum itself will burn, but the inside, the gypsum itself, will not. So as you know, if you were to crumble this, you've got two sheetings of paper on the outside, and in the middle you have your gypsum. So your paper on the outside is typically what will burn, not necessarily the gypsum inside. Prolonged exposure will cause failure of sheetrock, and then moisture in the material will evaporate, which can also cause something similar to spalling, but it's not necessarily spalling, but it will cause just pitting in your sheetrock to start losing some of that material, and then eventually will collapse, break, penetrate, allowing fire and anything else just to go through there and continue burning. Wood, most common building material, right? And we look on the left and we see just different types of woods, and some with good growth rings, right? The more growth rings, the stronger the wood. So wood is highly combustible. It does weaken when it's heated. Fire retardant chemicals that are added to it can also weaken the wood. And of course nowadays, right, in an attempt to not cut down our forests, and an attempt to be a little bit more save a little bit more money on our construction, we're using engineered wood more often. And so again, if I can sell the home for the same price but use cheaper materials, man, I get a lot more profit as a home builder. So I'm looking for ways to cut corners like this. And here you have some wood in the bottom picture that is just glue and laminate and thin pieces of engineered wood that are just combined together and pressed together and under pressure and temperature to form this lumber that I'm now using inside of houses. And unfortunately, these things burn much quicker than our legacy wood, or the wood that you can kind of see on the left there. That legacy wood is really dense wood. It's had years to cure, years to grow, and it's harder to have fire penetrate through that. It won't be as quick. Wood is now being engineered. That's important to understand. And here's an example of it. Here you have your joists that are spanning across the house there, and they're using this to build their home as the framing of the home. Right, again, I've made, you see the picture on the right, I've now made a I-beam essentially out of wood, particle wood, laminate wood, right? Looks just like a beam, functions as a beam, has some of the compression and tension forces of a beam, but much weaker in the sense of any type of penetration through it or fire penetration on it could cause this to collapse much earlier than your legacy wood or your legacy construction. Old wood versus new wood. Plaster on lathe. We don't typically see this in Deer Park much anymore, but plaster on lathe refers to a interior wall construction that was around in the 40s, and it consists of 4-foot long strips of wood. And that's called a lathe, which again, this is why it's called plaster on lathe. But your 4-foot long strips of horizontal wood, about 1 inch wide, are nailed directly to the wall studs. Then this lathe, you pour some plaster on it to fill the gaps and the holes, and it works really well. It works really well. You can add a primer to it, and then once that primer is complete, you can put some interior paint or wallpaper on it. It makes a smooth surface. It's rarely used nowadays except to repair existing walls or to refurbish historic buildings. But if you do happen to come across this, depending on where you end up going at some point in the future, keep in mind that this is something that adds additional headaches for firefighters, in the sense of if you have to penetrate through this wall to get to a fire that's behind it, it's going to be a lot harder. You're going to use more energy to work your way through this wall than if it had been made of sheetrock and studs. So understand that this can be an obstacle. It can also, though, on the positive side, it could help in preventing fire extension or fire spread if it is well plastered and all the holes are sealed in and so on. But just like that mortar, this plaster can begin to, we can begin to lose plaster during firefighting, which will expose the area between the lathe or the wood and can cause fire spread to occur. And so we could be allowing fire to go from one place to another much quicker to this type of material as well. Nowadays, lathe is found in a different method or different fashion. Typically, it's using a woven or welded or expanded metal, a mesh per se, and it's predominantly used for applications of Portland cement or plaster, stucco, that type of thing. So essentially, instead of using your lathe wood, you're using a lathe fabric or a lathe metal woven screen or net. You put that over your studs, and then you apply some sort of plaster or cement or stucco. I'll show you a picture over here in the next slide. Here's typically what that looks like. This is expanded metal lathe, and we do find this in many places throughout the city. Most common, 7201 Spencer apartments. You can find this type of construction finish on the outside. Usually it's almost like a stucco. And so what it does, the bad part about this is if you're trying to get to a hidden fire, which we've had hidden fires behind these walls, you have to go through a metal mesh, and you have to cut through that metal mesh. You have to cut through that stucco or plaster or Portland cement in order to get to the other side of the wall. So again, it's adding an additional obstacle for you when you're trying to tunnel through to get to that hidden fire. Shiplap. Shiplap, most people confuse shiplap and plaster and lathe. Shiplap comes from its original use as waterproofing wood paneling for ships. Shiplap again. A rabbet or a groove is cut at the top and bottom of each wood plank and allows the board to kind of lock into place, almost like a Lincoln log in that sense, but not necessarily cut like that. But it allows it to fit snugly, simply just like they'd use on a ship. And when installed horizontally, as most often you'll see, this makes them perfectly spaced and creates a highly effective barrier against wind, water, and other elements. So if you look at the photo on the left, you can see the shiplap in place. It's not painted or anything, but you can see that they are spaced evenly. They're interlocked to give you that weather resistance that you would seek as a homeowner. But you go down to that fire, the other picture down there, this is a fire that one of our neighboring cities had not long ago, and you can see some shiplap just to the right of that photo. So although it's helpful for your walls and it's helpful to keep your weather out, and it adds some structure and strength to your walls, it also is combustible. It's part of the fire. It can burn as well. And if you're trying to get through it, either to escape from one room to another during a hostile fire condition, or if you're just trying to get to some embers on the other side, you could see how shiplap on the walls could slow your progress, could create an issue, can hold heat in that room more. And if you were to find it on your ceiling space and you're trying to open up an opening above your head, you could see how much work it would be needed extra to penetrate through it. Cast iron. We don't really see cast iron here in the city of Deer Park, but we might not necessarily, well, we don't just stay in Deer Park when we're fighting fires. We go to our neighboring fire departments area, and they may have cast iron architecture, especially in those historic main streets. LaPorte has a main street. I'm not so sure that Pasadena has one, but again, we may be going elsewhere where they may have this cast iron architecture. Cast iron was used most popular in the 1800s, can be used in columns and arches, sometimes as a support to the brick arch. Again, most commonly found in historic buildings, including refurbished buildings. Cast iron is not usually used in beams. It has a low tensile strength and will lose its strength quickly in fire. This can result in a rapid collapse, and this is heavy. This cast iron is heavy. So picture being knocked on the head and not wearing a helmet with this. It could be fatal. Sudden cooling from firefighters' water can cause cracking due to thermal shock, which can result in failure of the structural member. So again, we're adding additional forces to this to this material during firefighting operations, and we are in there trying to do good, but our good can also have a unintended effect on some of these building materials. We're going to move into building construction. It's important for you to understand all 5 types of building construction. I've seen in other textbooks where these are broken down furthermore into 1A, 2B, that type of thing. But we're just going to cover the surface of these 5 construction types or construction categories. Type 1 construction is also known as fire resistive construction. These are all structural components must be non-combustible. It's used for large numbers of people, buildings that house large numbers of people or that are tall or large area. Think of downtown Houston. Think of the World Trade Centers. So what is fire resistive in these, or what is fire resistive? The meaning of that is it is immune to the effects of exposure to fire of a certain specified severity and duration. So we're not saying these are 100% fire resistive. What we're saying is it'll give you some fire resistive properties for a period of time. Now, how much time that is dependent on the material, depending on how much was what temperatures are encountered during fire, that type of thing. Some strengths of type 1 construction: the highest level of protection from fire development, spread, as well as collapse. So it does give you less chance of collapse. All structural materials composed of non-combustible or limited combustible materials with a high fire resistive rating. Again, it's not 100%, but it is a higher rating than most construction types. Components such as the walls, floors, and ceilings must be able to resist fire for 3 to 4 hours minimum. It's expected to remain structurally stable during fire and considered to be the most collapse resistant. Structural components do not contribute to the spread of fire, but contents do. So in this type of construction, again, your structural components are fire resistive, non-combustible, and typically they will not add fuel to the fire per se. It's the contents of this building, your carpet, your fake plants, your papers, your desks, everything else that you find inside, your contents that often add to the fire load. And often employs fire protection systems and fire rated assemblies. So you'll typically find fire sprinklers and FDCs, your fire department connections, your standpipes, that type of thing in this type of construction. The weakness, though, is that on these structural components that have fireproofing that allow this to be fire resistive or to resist fire for a period of time, that stuff over time may be removed, exposing the steel. And if that happens, then you don't have a true fire resistive structural component. You have an exposure of it, and if heat gets to it at that point, it could cause it to expand or contract, or it could potentially add to fuel load. Spalling of concrete is possible under prolonged attack by fire. We understood that already from the previous slides. The compartments in these types of constructions can retain heat, and that can contribute to the potential for rapid fire development, especially if it's ventilation induced. Meaning, if you've got a lot of heat that's contained within this room, and you suddenly introduce air, it could cause a rapid fire development. Roofs are extremely difficult to penetrate in these type of buildings. They're typically hard to get to first, and then once you get to it, you've just got a lot to cut through in order to get a good ventilation hole working. Windows in these type of places may be difficult to open or ventilate. Some of these are really strong panels that you can hit with a Halligan bar and will not crack or break. So some of these are very well built, especially in areas that are prone to high winds. They do have this type of construction do have wide open floor plans that can facilitate heat, smoke travel, and rapid fire spread. So picture a long office floor on one of these buildings, how it can be wide and open, and the only thing that's separating this wide open space is cubicles and an occasional office or an occasional restroom. Otherwise, wide open, and wide open is not necessarily good for fire. Fire love will take advantage of those wide open spaces and will run and find content and material and all that stuff to burn. There is a potential for vertical fire spread through unprotected poke-throughs, and this is really in all types of construction. This is a point to understand, is that when we ask our builders or our service technicians like cable and internet and telephone to come in and install something, in order to get it from one room to another, they typically have to create holes to run those wires and so on through. And in doing so, if they do not plug them up with something that is some type of fire that is non-combustible, if they don't plug those holes up around those wires, then now you have potential for fire spread through that area. And so then you don't have true fire breaks because of stuff like that. Type 2 construction is non-combustible. All structural components must be non-combustible. Fire resistive requirements are less stringent than type 1, so it's one step below type 1. Structural components contribute little or no fuel. Fire severity is determined by contents, just like the other one. Most common in single-story warehouses or factories. A lot of the buildings we find on Georgia are these type of constructions, the type 2. I've seen some textbooks classify the difference between type 1 and type 2. What they mention in those textbooks are, hey, if the structural components doesn't have fireproofing, then it's a type 2. If it has fireproofing, it's type 1. And although that is somewhat true, it is not always the only indicator of a type 1 or type 2 difference in construction. Weaknesses. Unprotected metal components make this construction type prone to early collapse. And we talked about the fire that we had, where I talked about the metal being expanded because of heat and pushing the walls out and away, causing a potential collapse. Combustible products used for built up roof materials, so your various layers of roofing on top, might be like your insulation foam or your asphalt or your felt paper, rubber. They all can be very flammable and can lead to a separate fire above and below the roof, which can spread as well. So if you arrive and it's a type 2 construction room and contents fire, and the fire breaks a window and it starts heating up the roofing material, you can have a separate fire because some of that material is flammable. Some of the material fuels there are flammable. Failure to cool the ceiling area early will allow heat to weaken unprotected steel, prompting potential failures and collapse. I think I've mentioned that three times now, is that steel, unprotected steel, expands and contracts, and if we do not think about applying water early on to this steel, then we are risking a early collapse on us as we are working in there. Type 3 construction is ordinary. Per se, they call it ordinary construction. So it's another way to determine whether it's type 3, or you call it type 3, or you call it ordinary construction. The words are interchangeable. Used in a wide range of buildings. Think of Main Street. Your main streets as you're driving through some of these old towns. Masonry exterior walls support floors and roof, usually limited to no more than 4 stories. Limited fire resistance requirements. This has 2 separate fire loads, which is the construction material and your contents, ordinary construction. Some weaknesses in type 3 construction is that common party walls, which party walls is a wall that's shared between one side of the occupants, and on the other side there's a different occupant, and y'all are sharing the same wall. Those are party walls. Joists may sit in the same wall socket, which allows for horizontal fire extension, threatening structural stability. So what you're doing is it's almost like a balloon frame. You're adding a void space that allows fire to travel. Attics may exist, allowing for fire spread. Older type 3 structures may have undergone renovations. So this ordinary construction, it's called ordinary because it's the most often found. It was a construction that was most often or ordinarily used, which is again why it's called ordinary construction. But because this was something that was used quite frequent in the past, it may now not serve the needs that we want as tenants or as residents. So typically these buildings or these type of construction have undergone some sort of remodeling, and that remodeling may have caused more voids, may have caused weaknesses in the building itself, all in an attempt to get us what we want as the new residents. So again, when you convert these type 3 structures to something more modern and you modernize this building, you may be causing some weaknesses and allowing some voids for fire spread. In some cases, rain roofs may have been installed over existing flat roofs. Sometimes it is much cheaper to build a roof on top of another roof rather than paying folks per hour to remove a roof and then install another roof. If I can avoid removing the roof, I can save a little bit more money that way, in some cases. Type 4 heavy construction, heavy timber. New Type 4 construction is rare. You gotta remember that wood is expensive nowadays, and solid wood, like what is used in heavy timber construction, like in churches and other large open area buildings, having big thick pieces of wood is pricey and hard to find. So therefore, it's rare to find new Type 4 construction being built, just because it's so expensive or harder to find. Type 4 construction is that in which building elements are mass timber or non-combustible materials and they do have a fire resistance rating. Largely constructed using large pieces of lumber connected using metal plates and bolts. This is what you would find in your large cathedrals or large churches early on. Weaknesses are that the structural members are very big and thick type of thing, and if they can contribute to the fuel load, and if they do fail or release, those are large pieces of lumber that are falling on firefighters. Additionally, if fires pass the initial stage, it's very difficult to control and can burn for a prolonged period of time because this wood is so dense. It's hard to get to the middle of this stuff sometimes. And then finally, we get into Type 5 construction. This is what is most commonly utilized in our construction nowadays for residential and even commercial. This is just essentially a matchbox, right? Picture a box of matches. Picture all your little matches being your studs and your rafters and your joist here, and you essentially have something that's really easy to burn. Now, Type 5, or wood frame construction, this is how it's otherwise known, can be balloon frame or can be platform. The bottom photo shows the difference between your framing methods of balloon frame or platform frame. In balloon framing, which is still being used today, but was much often used prior or years ago, is where your studs actually form a void all the way from the bottom, from the foundation to your attic space. So think of a tunnel. Think of a rat maybe or a mouse that's climbing up through from the foundation all the way up to the attic. Okay. If he can go directly from your foundation to your attic by climbing that wall, that is most likely a balloon frame in that example. Right, but if he can't get to the attic because there is a horizontal platform, then he can no longer go up into your attic space. And this is good. Balloon frame construction allows fire to spread through that void space all the way into your attic and allows that fire to spread into your attic space a lot quicker, whereas your platform construction prohibits that fire from spreading up to the various levels because it hits that platform and doesn't have anywhere else to go. Wood frame construction do collapse more frequently, especially with new lightweight construction methods, and can rapidly become fully involved, especially with the contents that we may have inside. So weaknesses, obviously the wood will burn. Older buildings may have dry rot, water damage, or damage from wood-boring insects like termites. So these older homes that are Type 5 construction can already have some weaknesses before the fire even hit it. Void spaces are common and in balloon frame can be extensive. Renovations are commonplace in older structures. People want to add additional rooms, additional items to their home, and this could create weaknesses. Vertical voids beginning in the basement can lead to significant vertical fire spread to the attic. We talked about that in your balloon frame. And then if we're using Type 5 I'm sorry, if we're using engineered lumber in type 5 construction, which we are now a lot more, then it is much weaker, quicker to burn than the legacy stuff, the older stuff. That is not good for us when this house can burn a lot quicker. Lightweight wood construction elements techniques have redefined wood frame construction, making modern wood construction more susceptible to fire spread and early collapse, and is a danger to firefighters. Lightweight construction uses lightweight materials, cheap connectors that still accomplish the task, but can spread and cause fire and collapse and weaken much quicker. Now this is a little diagram, I guess, of spread and collapse potential between the different types of construction. This doesn't hold to be 100% true, but it's a good mental picture that you ought to have, so that when you make a scene, you can think of two things right off the bat. What is my fire spread potential, and what is my collapse potential? Knowing this before you get off the truck can be useful, because now you're looking for signs to justify this. So for fire spread potential, typically you have a smaller chance of fire spread as you go down that list. So type 1, then type 2, then type 3, then type 4, then type 5. In that order, your greater fire spread is going to occur in your type 5 wood frame construction than it would in your type 1 fire resistive construction. On the other side, your collapse potential, this is all over the place. It doesn't go in any type of numerical order, but typically your collapse potential is most likely to occur in type 1, less likely to occur in type 1, and greater to occur in your type 2 construction. Okay, and in between that you have heavy timber, wood frame, ordinary. So your collapse potential is very small in your fire resistive construction than it is in your type 2 construction, where that may fail much quicker. Again, these are generalities, not 100% true, but they are fairly accurate. So we're going to talk about building components now. So foundation, floors and ceilings, roofs, trusses, walls, doors and windows, interior finishings, and floor coverings at this point. So foundation, we know what the foundation is. We can apply this to various things when we think about foundation, but the foundation helps hold everything else in place, right? Talk about your grandma or your great-grandma being the foundation that held everybody together. We'll think of it in the same way. Your foundation here helps hold the system together. It ensures that the building is firmly planted, helps keep all the other components connected. Weak or shifting foundations can cause a collapse. So think about down here in Texas, just your soil being compressed during times of drought, and how your structure can change. Your doors, you might have trouble shutting your doors because your foundation has shifted, and due to not enough water in the soil, and then you start adding water to the soil, and then your home shifts again. Some of these shifts are designed. Your foundation is designed to be somewhat of a floating foundation. Say somewhat. But it's not designed to. It's not designed to take large movements, and when you take large movements, it starts to weaken your studs and your walls, your sheetrock. Starts making cracks in there, and all that stuff can again contribute to early collapse during a fire or fire spread. But keep in mind, floors and ceilings and their void spaces can contribute to fire spread. So in this picture, you can see your wall studs, and you can see insulation in those wall studs, and fire can spread in between those wall studs up or down if it's not platform frame. If it's platform frame, it will most likely stop there. But also keep in mind that your floors are made out of wood as well. Your floor joists are made out of wood, and those can burn. If you've got fire underneath, those can easily burn. If you're standing on top, you could see how you could essentially fall through if there's a fire. So this picture is over dramatized, but it does serve a purpose to know that those can burn as well. Now we're going to talk a little bit about roofs. We're going to talk about roofs and just know that they're not designed to be as strong as floors. There's three types of, actually there's more, but the three primary designs that we're going to talk about are pitched roofs, curved roofs, and flat roofs. So here we have different types of pitched roofs. We've got hip roof. We do have houses that have this hip roof. We have gable roofs. We have mansard roofs, and then we have lean-to roofs, like you see in those modern homes. Can be sloped or inclined. Most likely they're sloped or inclined to allow water to come off of it. Usually supported by rafters, trusses, and requires some sort of roof covering, either metal sheeting on your roof, or tiles for that Spanish look, or even shingles. Here's a curved roof used for large buildings that require large open interiors. Sometimes these curved roofs are very, the pitch is very, very low that you can't even tell it's a curved roof. It may almost appear flat. But these are often used in warehouses, supermarkets, industrial buildings, and they're usually supported by bowstring trusses or arches. And that is, you can see right under that curved roof, that is the bowstring truss or arch that is holding that up. Flat roof, usually found on houses, apartment buildings, warehouses, factories, schools, and hospitals. So they're not always just on commercial properties. They have a slight slope for drainage. Can be very difficult to penetrate through when cutting due to layers of roofing that has been added over years, or the type of material. Sometimes these areas feel really spongy when you're walking on, so you should as practice get up on roofs to feel the differences in them, so that when there is fire, you know, okay, this is a normal feeling or this is abnormal feeling and we need to get off. So keep in mind that some of these roofs, flat roofs, have openings in them that you can utilize for ventilation purposes, but also keep in mind that some of these openings can present a hazard to you during smoky environments. You could find yourself falling through one of these skylights or other types of openings. Flat roof construction techniques use either I-beams or trusses. Most often they're trusses in commercial, I-beams in residential. But we were talking about those open web steel trusses or bar joists back on type 2 construction on that side. And we talked about how they're often used for support. Most coverings are highly combustible. Ventilation may involve cutting through many layers of roofing, like we already talked about. But notice that in this picture down here that these are non-fire-proofed, which again, if one of our priorities is not to get in there and quickly cool that area under that roof, those bar joists, then those can easily heat up and cause expansion and cause failure of that system. So trusses, again, I'm going to talk about three types of trusses. Trusses are triangular geometry, which create a strong rigid structure. So they're essentially triangles that help form some strength to the horizontals, and can be prefabricated out of wood or steel. We'll talk about the three here, and there's many more, as you can tell, but parallel cord is something we often find, again, in our warehouses or type 2 construction. Pitched cords, something that we also find when on pitched roofs for commercial structures. Here in our area, you typically don't see metal pitched cords. Typically these are made out of wood. In our attic space, bowstring used for curved roofs. Do I expect you to know what type of cord we're utilizing in a house when you arrive on scene? No. But what I am trying to emphasize here is that there are different variations of them, and to know that when you weaken part of this truss, you create a weakness in the whole truss that could lead to early collapse. Again, that gives us the point that we need to get to our fires quick. We need to put them out quick. We need to find them quick. We need to get the people out of there quick before fire creates additional hazard. Here's some more common timber trusses that are often found in residential as well. One thing in this picture that I do want to talk about are these gusset plates. These gusset plates are the metal things that are connecting woods together, and typically they've got little spikes on the wood side that kind of dig in there, almost like cleats. You secure these in with some screws or a nailer, and it allows for multiple pieces of wood to connect easily. These are somewhat flexible, so they can fold and bend a little bit to get you the securement that you need. Unfortunately, these connector points, as they are exposed to heat, like any other metal, they expand and contract, and those little cleats, as well as the nails or the screws, can begin to back out, which means your wood is no longer connected as strong as it needs to, and it's still holding up a lot of weight, and because of all those things combined, can now lead to a collapse. Walls are the most visible part of the building, constructed a variety of materials. Some are load-bearing, some are non-bearing or non-load-bearing, and some are specialized like party walls. Load-bearing walls versus non-bearing walls. This is important for you to understand, because if you're going through a wall or you've been tasked to breach a wall, you typically do not want to cut through a load-bearing beam or a load-bearing stud that's holding up a load-bearing wall. Because what a load-bearing wall does is it gives structural support to the structure. It could be an interior space or exterior space, and they support both the dead load and the live load of the home. And damaging it can cause a result, or can result in a collapse. So dead load are things like your AC units that are in your attic space. It is the weight of the structure. It is the weight of the material on the home itself. Your live load is your additional load on the structure, and this could be the people inside of it. This could be your furnishings that can be moved around the room. These are the things, typically things that are non-stationary, or they're more mobile. So those are the things that can add to the load of the structure. Your non-bearing walls support their own weight. You can remove these or breach through them without compromising the integrity of the structure, and they can also be found interior and exterior as well. Here's just some pictures kind of depicting load-bearing versus non-load-bearing. Really hard to see unless one, you're there during construction phase, or you're pulling sheetrock to see how they're tied in. But typically again, not 100%, your exterior walls are the studs and the system that are holding your exterior walls are typically load-bearing, and those inside are typically non-load-bearing. Again, don't leave here thinking every wall inside my house is non-load-bearing and everything outside is load-bearing. That's just not the case. You really have to see how they're tied in and to really understand which one's a load-bearing or non-load-bearing. But just understand the load-bearing ones hold up a lot of the weight of the structure. Your non-load-bearing walls you can remove, and it will not cause any issues with the structure. Here is an example of a firewall. This firewall looks like sheetrock or gypsum, and as you can tell, it's been penetrated through for some reason, and again, that allows fire spread through it, where that firewall was designed to stop fire from going from one area of that attic space to another. It now has a hole, a couple of holes that now allow fire spread through it, and it defeats the purpose of it. We're getting towards the end of the presentation now. Probably have less than 10 slides left, and the rest of these are just going to be additional tidbits of various pieces of information that deal with construction that are important for you to know. So truss roof collapses have killed many firefighters in the past. The trusses, as you saw, come in many styles and shapes. Wood trusses are commonly used for roof assemblies and floor assemblies, meaning holding up the roof and holding up the floor, maybe from the first to the second. Steel trusses no less susceptible to collapse than wood trusses. So any weakening in that system, whether it's a wood or steel truss, can create a collapse hazard for firefighters. Wood trusses provide a large surface to mass ratio, fuel load, and void space, three of the worst structural collapse contributors a firefighter will encounter during structural firefighting operations. So that wood is being exposed at various faces to the fire, to the heat, contributing to fuel load. It allows for void spaces in between it that allows for fire spread, and it can get involved in the fire itself, and those three things can lead to firefighter killers. Again, void spaces are made due to trusses being put together, and then the walls, and then the sheetrock and the structural components, and then your walls. There's just void spaces that are naturally created. You can't block out every single space. You can't fill it with something. That would become very expensive if you try to fill every void space within a house. So there are void spaces, especially, and I'm not going to talk about this in this presentation, but when we start looking at knee walls within a house, those knee walls, KNEE, knee walls, we have various homes in our house, in our district, in our area, that have knee walls, and it's able to be, you're able to easily see that a house has knee walls from the outside, but you don't know unless you're looking for it. And those knee walls create void spaces, and fire likes to travel in those void spaces, and you may forget to look in there when you're searching for fire spread. And if you don't look in there, then you're never going to put this fire out. So knee walls, look those up, understand what those are. In type 3 ordinary construction, voids are numerous, again, especially if they have been remodeled to meet the needs of the residents. Stairs, a lot of folks think that these stairs are really solid, and as I'm going to present now, they're not. These are typically built off-site, and they're hung in place with metal strapping. Stairs are made with lightweight engineered wood products, and they fail very quickly when heated. So if you go into a house and you've seen that the stairs have been exposed to fire or on fire, that may not be the route that you travel to get up to the second floor. Now, if the fire was in a complete other room and your stairs have not been touched yet, then yeah, it would make sense that you can't climb up those stairs because they haven't been weakened any. But keep in mind, these stairs are not structurally sound. They're brought in and hung in place and reinforced around it. Parapet walls. You'll see the pictures on the right are a gas station, fuel station here on Underwood and X Street. A parapet wall is a vertical extension past the roof. It's used to help hide stuff that's on your roof, like your AC stuff. Many folks put this on to modernize their building. Rather than their building look flat from the front, they now add these parapet walls where they can hang signs and put their name of their building, and it makes it look more modern and more appealing. These are typically freestanding with very little stability, which means they are easy to topple over when forces are acting upon it or during fire. These are easy to collapse and have known to collapse on firefighters. So they're not always just made out of wood. Sometimes they're made out of plaster and other type of material like that. And sometimes, like you see in the photo on the left, it may be adorned with some brick, or I'm sorry, some stone, or something like that to just give it a different appealing look to it. Just keep in mind that when you're trying to access the roof using an aerial ladder or ground ladder, there's going to be a drop from the top of that parapet to the actual roof line. Could be 4 feet, could be 6 feet. So be anticipating that, and sometimes that may mean you have to bring another ladder with you so that you can come off the tower or come off the ladder down onto the actual space. So some reasons for building collapse. Poor fireproofing. We talked about how we make those holes for our utilities and our cable lines and TV lines and all that stuff. That's poor fireproofing. It could also be poor fireproofing around our structural components, like fireproofing or lack of fireproofing on our steel. If we don't cover those up like they need to be, or if they're chipping off, or if we've taken it off, it can create a building collapse. Lazy and cheap building, right? That's one thing that it's hard to control, is how much time people are actually devoting to their trade, either in learning how to do it correctly or minimizing shortcuts. So lazy and cheap building and unskilled labor all can contribute to collapse. If we're trying to get this job done as quick as possible, as cheap as possible, then there may be some shortcuts in material and in labor in how they perform their job that could cause collapse. Forces of weather can cause building collapse, wear, tear, deterioration. Fire will obviously have an effect on it, especially the energy and pressures that are associated with it. And then additions and modifications of the building that we typically do, right? Every year we want to try to add a new thing to it, a new room, a better window, a better shingle, and those things all contribute to building collapse. Some collapse warning signs to anticipate collapse. So if you're out there on the fire ground and you're looking for potential fire collapse, we look at deterioration of the mortar joints and masonry, like we learned on one of the first slides. We look at the overall age and condition of the building. Is it a new building or is it an old building that's been a while? What are the cracks showing us? You know, what kind of crack is it? Is it a surface crack, or is this a crack that's been created because of your bar joist that has expanded? Is there signs of building repair, meaning have there been some remodeling currently in progress where fire can now spread more because they've knocked down a wall to make it a larger room? Are there bulging and bowing of the walls on the outside? Are there sagging floors? Is there just such a large volume of fire that you can anticipate that there is going to be a collapse because of how hot it's burning or how long it's been burning? And don't forget our firefighting operations. We can contribute to collapse. Water weighs 8.33 pounds per gallon, and we're adding hundreds of gallons sometimes to these fires, thousands of gallons sometimes, and that weight has to go somewhere. And you're adding additional forces on this house that's been engineered not to take it. Keep in mind, new building construction, here in our city, we've got a lot of buildings that are going up. New building constructions are really unsafe during construction and remodeling and restoration. They don't yet meet the fire codes during the construction phase. Now, once they're complete, then they most likely meet the fire codes. They've got everything in place, the extinguishers, the sprinkler systems, everything's well protected and fireproofed and insulated and all that good stuff that makes it a safe building. But during construction, it's not safe. And as you can see, that photo on the left, that shows a fire that happened here in Houston, not too far from us, where during the phase of construction, fire quickly went through the open spaces, went through the building material, involved equipment that may have been in there, involved chemicals, and there was not yet a suppression system in place to prevent that from going any further. So these new building constructions can be or should be an issue we pay attention to during the building phase, so that we can learn what the building looks like early on, and also keep in mind that people building these places are adding material and pallets of stuff that could overload certain areas of this building and that you may be working under to put out. There is no time limit for firefighting operations, meaning when it comes to collapse, it could happen quickly, it could happen down at a later time on this fire scene. So don't think, oh, if 10 minutes, if it hasn't collapsed yet, then it won't collapse. That's not true. But there are some things, some truisms, or some things that are common that have emerged from research, and that is that the lighter the structural elements, the faster it comes down. Lightweight construction will come down quicker than legacy construction. Again, this is a truism. Doesn't mean it's 100% true, but we're going to say it's greater than 50% true, 70% true maybe. The heavier the imposed load, the faster it comes down. Okay, if I have a heavy AC unit up on the roof line that's been burning, that most likely will come down first, then a little sheet metal windmill that may be up there that's not imposing such a huge load. Wet or cooled steel buys time. Again, getting in there, applying a stream up in that area of the bar joist will buy us some time to prevent collapse. Gravity and time are constants. I mean, we can't change time, we can't change gravity. They're going to work for us or against us, so we've got to be Johnny on the spot in identifying things and getting things mitigated. Again, there is no window of time. It's not going to happen within the first 5 minutes every time, but it could happen within the first 5 minutes every time. So time is not a good predictor of when this collapse will occur. The IC or the incident commander, we need to predict these collapses proactively. We need to think about what signs the fire has shown us, the building construction method, the forces that have been imposed on it, the tactics that we've implemented on it. All this needs to be utilized to predict collapse early on. And that may mean we build a collapse zone. And the collapse zone is 1.5 times the height of the building. So that means, like in this building, it's 1, 2, 3, 4, 5 stories tall. So we would go 1.5 times that height, 1.5 times 5 stories. And that ought to be how close we get to that building. And that's textbook. The issue is sometimes we need to get up close to that building. Our trucks don't have that length. Our lays can't be that far away. And sometimes we need to be very intimate with that building, get up close and personal. But knowing which areas we can and which areas we can't is what's important in preventing the dangers to firefighters. When we establish a collapse zone, we cannot have firefighters or equipment wander in there, because if we designate a collapse zone is because we've noticed that something has a potential of going wrong in that area, and we don't need to be in that area. Here's just a minor collapse at a fire we had over on 13th Street in Center years ago. This roof had had many layers of roofing added to it, and this fire had been burning for some time before it penetrated through the multiple layers of the roof that allowed someone driving by in the morning to see it, 2, 3 in the morning to see it, and they saw a little bit of flame that penetrated through the multiple layers of the roof. Well, eventually fire department arrived, encountered heavy fire on the inside, and eventually there was this wall collapse on the exterior. No one was hurt, but it could show you how a firefighter walking along that route, not paying attention to building signs of collapse, could easily find themselves under that load. And depending on how they land, and depending on how much weight and what else was on top of the roof that fell down on there, could mean whether that person goes home with just a bruise or not go home at all. So we really need to be cautious about these structures, how they're built, what the fire does to them, how we're approaching, what tactics we're using. And again, here's another view of the collapse. And that will conclude my presentation. So I encourage you, again, if you have any questions, since this is not a live class where you can just raise your hand, I can call on you. Please write down any question that you have come up with during this presentation. Get with me so we can discuss each of those questions so that you can leave here very similar to if we'd been under the same roof having this class in person. I appreciate your time. Thank you.